Thank you. So I will discuss stiffness versus a strain for architecture to infill for additive manufacturing. This studies has been done together with our co-workers, Martin, Marie, and Yi Qiang. There are many multi-skill structures in nature. One example is the bone structures, as shown by this image. For different loading conditions, bone has a different microstructure shown by this image. 20 years ago, we used topology optimization, try to seek the stiffness optimal microstructures for triaxial loadings. He came up with this closed cells plate microstructures, which has a stiffness at Hessian-Strickland bond. Compared to the stiffness optimal structures, we can see the microstructures in bone structures are definitely not stiffness optimals, besides other functionalities in the bone structures. So what about the buckling strengths for those structures? I will try to answer these questions during this talk. And nowadays, this open cell latex, truss latex is commonly used as an infill in additive manufacturing, as shown by this two image. On the other hand, plate structures has been demonstrated can have the stiffness optimal properties as Hessian-Strickland predict. On the other hand, open wall truss latex shows more inferior performance in terms of stiffness. And recently, my colleague managed to use optimization to obtain nearly stiffness optimal motor scale structures, use these open wall microstructures. And all this study has proved plate lattice structure are stiffness optimal, while truss lattice are not. So now the question is, what can we use for truss lattice microstructures? How about their strength performance? I will try to answer these questions during the talk. So first, let's discuss a little more details in stiffness optimal microstructures. Briefly, it has been demonstrated these rank 3 microstructures are stiffness optimal for single load case in 3D problems. And as shown here, the optimal rank 3 microstructures has a length scale separations. Depending on the load conditions, maybe up to 6 laminations needed in order to get the stiffness optimal structures without periodicities. This image shows how one can form a rank 4 laminate. And recent study, both from our group and also Baggers, shows actually without length scale separations, single length scale microstructures can also obtain nearly stiffness optimal performance, which meet the Hessian-Strickland. This shows the simple cubic plate structure, isotropic plate structures. And this image shows the corresponding open wall truss counterpart. As already mentioned, truss structures is not a stiffness optimals. Our group has did intensive numerical optimizations to seek stiffness optimal open wall lattice and arbitrary load conditions. This image summarizes the comparison between closed plate structures and open wall truss latex. We can see in general, open wall truss latex shows inferior stiffness in a range of 1 to 3. In the load conditions, if all the plate is fully loaded, then the optimal open wall truss lattice shows the maximum stiffness inferiorities, which approach to 3. For example, in this case, and also in this case. However, only at one case, which is and a single uniaxial loadings, the optimal single truss microstructures and the optimal single plate, this shows the same stiffness response. As I already mentioned, one need to have the 6 lamination directions in order to achieve stiffness optimal microstructures without periodicities. However, if we need period microstructures at the same time and isotropic, then we need at least 7 laminate directions as indicated by these 2 configurations. Those colors indicate different lamination direction where the plate placed. So now the question is, how important are the 6 lamination directions? So we did a study to optimize plate structures for different lamination directions. This is for 3, and this is for 4, and this is for 5. And the y-axis indicates stiffness optimalities for optimized microstructures. One can see as the lamination direction increased, the stiffness optimality also increased. But however, at lamination direction 3, we already get quite a good stiffness optimalities depending on applications. One can choose different numbers of lamination directions. So I have discussed the stiffness optimalities for different microstructures, and how about this microstructure performance in terms of buckling strength. We evaluate the material buckling strength via microstructure stability studies, use linear buckling analysis, assume infinite periodicities, and microstructures are analyzed using the block of Floquet wave series. And in order to capture all the possible all the possible buckling mode, and the material buckling strength actually is determined by the lowest possible buckling factors stated by these equations. We consider 5 different microstructures: isotropic plate structure, which I have discussed, and simple cubic plate structures, and the corresponding open wall truss counterpart. Also the second hierarchical simple cubic plate structures. This image shows the band diagrams for different microstructures, and this dot shows the corresponding critical buckling point, which also is which means the lowest one is the material buckling strength. And together with the critical buckling mode profile, we can see from this plot, actually the second hierarchical simple cubic plate has the highest buckling strength, and different microstructures has a different buckling strength. We studied the material performance, the material microstructure performance with a different volume fraction down to the very low up to 50%. Then we came up with 2-term interpolations for Young's modulus and buckling strength and uniaxial compression and yielding strength. As one can see, Young's modulus and yieldings has a linear volume fraction dependency. Different with them, buckling strength has a higher order volume fraction dependency. More interestingly, truss lattice shows lower volume fractions, lower volume order dependency than the plate lattice. This indicates buckling strength favors open wall truss lattice at low volume fractions. One thing I would like to emphasize, these 2-term interpolation schemes give accurate estimations of material properties up to 50%. So now we plot for different microstructures. We plot the stiffness versus strain HB plot. Here, in this plot, this kink indicates the transition point between buckling dominant strains at a low volume fraction to yielding dominant strains at a high volume fraction. And here we use epoxy as the base materials, and the solid line indicate the ideal microstructures, which has the stiffness bound and yielding bound. And the black dot indicates the base materials. In this case, we can see non-microstructures, no matter which hierarchical you consider or which microstructure you consider, it can never beat the performance of the base material. This plot shows the specific stiffness and specific strain plot. And same as this plot, the base material has the best performance. So by only studying stiffness and strain index, we cannot show the optimality of the microstructures. In order to investigate the optimality of the microstructures, we try to design a beam by a mass minimization problem of a beam in bending. And this plot shows the multi-objective plot. This is also one upspeed plot. You see the performance for isotropic open wall truss lattice and closed wall plate lattice. And this axis shows the corresponding wave savings. For a beam with original length L, we can see it's the beam here, this beam. And then this long span beam actually favors truss lattice. And if we shorten the beam, then the truss lattice and the plate lattice, their performance become similar. If we get even shorter beam, then the plate lattice will outperform than the open wall truss lattice. So this is a half length, this is the fourth length. This is the also length. This, to summarize, for long span beam case, truss lattice is favorite. For short span beam case, plate lattice is a favorite. However, if we take it into hierarchical into account, as shown here, this is a second order hierarchical isotropic plate lattice. It will beat all the single length scales microstructures, has the best performance among them. We also use topology optimization to design microstructures for extreme stiffness and stabilities. Here we focus to design single length scales, isotropic microstructures. The length scales is imposed, use length scales controls. We don't consider stress constraints. The first row shows the topology optimized microstructure. Here is for volume fraction of 20%. And we further simplify the topology optimized microstructure configurations, use the feature-based parameterization and perform shape optimizations. This is the result we get. And we can see, compared with the reference designs, the topology of the optimized designs performs better in terms of buckling strength at a small cost of the stiffness. Of course, due to the geometric constraints in the shape optimization, it performs slightly worse than topology optimized designs. This image shows the stiffness optimized microstructures. One may notice actually it's not a stiffness optimal, it's sub-stiffness optimal. It's due to the length scale we imposed in the optimization for 20%. It's much higher than the plate thickness. This shows the buckling strain optimized microstructures. So in the mass minimization problem, this image shows the corresponding performance comparisons between the optimized microstructure and the reference ones. Again, the optimal beam is built by epoxy. For 20% volume fractions, we can see we still get a better performance compared with these ones. But here we didn't, as I mentioned, we didn't take the yielding strain into account in optimization. If we do the same thing for the reference microstructures, that's the overall performance for different configurations. For a volume fraction 20%, we can see here we still get a better with sieving compared to the reference single length scale microstructures. If we build the optimal beam with a different microstructure, with a different base material, how do they perform? These figures actually summarize the corresponding performance. We can see the different base material may lead to different transition points between truss and plate optimalities. However, the general observation is still validated here, which means for long span beam favors open cell truss lattice, and shorter span beam favors closed wall plate structures. But for the transition variations due to the different yielding strengths to Young's modulus ratios. But one thing I have to point out, actually for TPU actually is not a good basement candidate in this optimization problem, because none of them can have an optimal beam which has a same width as a solid epoxy. Therefore, in this case, TPU would not be a good base material candidate. We also did volume fraction interpolations for one optimized microstructures. This image shows the corresponding performance. We can see for the compared to the single length scale microstructures, the shape optimized microstructures shows superiorities at a volume fraction from 1% to 10%. Of course, as I already mentioned, the second hierarchical plate structure performed much better. We also performed experimental verifications for the optimized designs. The microstructure actually, with several periodicities, is printed use TPU like materials, use the printer from Formlab, and we did a unilateral compression test. And this image summarizes the corresponding comparisons. This line, the solid line, indicates the experiment result, and the dot line indicates the numerical post-buckling evaluations, and the dashed line indicates the linear material predictions. And specifically for this case, we did a CD scan and did a post-evaluations numerically, and to see the corresponding performance. This is the performance for isotropic truss. We can see from here, actually the linear material buckling analysis can predict the buckling strength well. Compared to the reference isotropic truss, the hybrid optimized microstructures shows 3 times higher, close to 3 times higher buckling strength, and also a slightly higher Young's modulus. As in the previous study, we did accurate material buckling analysis. However, these simulations are extremely expensive. For unilateral compression along the material axis, it takes up to 100 hours for 24 CPUs to get the band diagram. And it can be even more expensive for other cases. So now the question, can we came up with a simplified model to estimate material buckling strength? This material buckling mode in both cases shows actually the critical buckling load is dominated by local member buckling. Therefore, we can classify the microstructure member set according to their laminate directions and perform a local member buckling analysis based on the stress at each local member set. Here we consider 2 boundary conditions, clamped and the simple supported. And this image shows the corresponding result. We can see actually the clamped boundary condition overestimate the buckling strength, and the simply supported underestimate buckling strength. So as we know, for the microstructures, each member set gets a stiffening from the neighboring members. from the connected neighboring member. However, the stiffening effect is not enough to clamp the plate. Therefore, we need a model in between. We propose a rotational spring models to take into account the stiffening effect for connected plate. Then this image shows the corresponding performance. We can see the simplified model perform better than the other two and have smaller errors. More important thing is the simplified model only take 5 seconds per member set. And compared with 100 hours, they are huge time savings. Use this simplified model. We studied the material property surface and rotation in uniaxial compressions. This is the stiffness surface, and this is a corresponding yielding strain surface for this two. And this is the buckling strings. Interestingly, compared to the plate, isotropic plate microstructures, this truss microstructures shows higher isotropic in yielding. That's because bar only take actual loadings. And most important thing is the buckling strength actually in both cases shows higher isotropy compared to the stiffness. If we study the microstructure configuration carefully, we will see actually this plate lying on the diagonal directions. Actually, it has a weak spot for neighboring because of the missing plate in the SC directions. If we split the SC plate into two and get the new configurations, here in this configuration, the front black plate has been hid for visualization. In this case, all the triangular plate will be evenly supported. And so now we analyze the performance of the new configurations. We can see in terms of stiffness, isotropy, there's not much change. Also, yielding is hold same. And now is the buckling strength. We can see the new configurations actually has much higher also isotropy than the reference one. And with this, I would conclude my talk. And here in this presentation, we show the closed wall plate lattice are 1 to 3 times stiffer than open wall truss lattice. Buckling strength or yielding strength favors open wall truss lattice for lower volume fractions. Optimize single length scale isotropy microstructures beat truss and plate for small volume fractions, and also for high yielding string-based materials. And numerical experiment studies violate the linear buckling modelings. And more important, we use a simplified model, the stiffness isotropy, and doesn't indicate buckling string isotropy. The new configurations shows more isotropic buckling string surface than the reference isotropic plate. The most important thing is we propose a simplified model which can have a huge time saving in terms of buckling string evaluations. For people who are interested in our studies, I give a reference list and highlight the most relevant one in red. Thank you for your attention.
Yeah, thank you, Fengwen Wang, for your presentation with these lots of studies which you showed us. So the presentation is open for discussion. I'm looking to the audience. I don't see at the moment the first question. So maybe I start with a question.
Yeah.
What about printability of your optimized structures?
Actually, you know, we did experiment. It's open. It's not closed cell, right? It's open cells, okay, and it's okay. We use the Form 2 printer. Use elastomer. It's print well, actually.
Mm-hmm. So this one is well printable, but you had in particular with the closed structures, you had many where I would have kind of doubts if they are really printable. So no,
in the slide I show the shape optimized designs, right? I do have for the stiffness optimal. Actually, it's a bulk modulus optimal. That is a closed wall. That cannot print. Therefore, for the experiment verifications, I impose the manufacturing abilities, make sure all the walls are closed. We don't have a closed are opened. We don't have a closed cell, so that the resin can release. And then we need a little bit of support. But the support is very easy to remove. I think it's okay.
Okay, more questions.
Yeah.
So maybe from the F&A. Okay, Paul.
Yeah. Again, I come with my naive questions here. In this diagram where you have stiffness versus strength, right?
Yes.
I mean, we have essentially 4 different domains, right? High stiffness, low strength, both high, and so on and so forth. I mean, are there possible target applications for all of these quadrants? Let's say, would we find applications where we want to have maybe low stiffness, so very soft material with high strength?
Like a soft robotic.
For instance, no?
Yeah, soft robotic, that's really, for the soft material, right? You want it to have extremely soft.
Yeah, but maybe the other quadrants, like, let's say, I don't know, low stiffness and low strength, there's maybe no particular application for that.
No,
right?
that's will feel, right?
Yeah. So, but it's not exclusively the target to have high strength and high stiffness, right? I mean, also other combinations could be.
No. That's why because in the purely stiffness and the string HB plot, you cannot see whether it's not optimal to use any microstructure because the base material has dominated, right? The optimal performance. Then it's really which one is optimal is really application to determined properties. Different applications maybe require different microstructures to be optimal.
I mean, to populate this diagram,
yeah,
I suppose you did, I don't know, thousands of computations or...
Oh no, actually, let me show you. I can show one. How can I show? A moment. Actually, it's
you need to share your screen again.
Yeah.
Okay, here it is.
Yes, it's this one, right? You see, we first have this volume fraction interpolation for material properties, right? As shows by this pane. Oh, can you see here? Then we have this. So we have this at hand. Then we have the we have the beam mass minimization problem. Thus, you can derive what is the optimal. Then you can have the plot.
Okay, so what you're saying is to produce these diagrams is not that time consuming. Yeah.
No, this plot is not that time consuming, but to come up with this two-term interpolation, it is extremely time consuming.
I see.
Actually, it's done by our PhD student Martin. It takes him almost 2 years.
Okay.
It's because there is a question.
There is a question from the audience, which goes, I think, a little bit also in this direction. Maybe I read the question. This is from Alexander TS.
Yes.
Thank you for the interesting presentation. I have a technical question. What kind of software did you use for generating the lattice structures, the simulation, and the topology optimization? Was commercial or special code used?
There are several questions as combined, right? For the reference configurations, right? All the studies done by Martin, actually, we have used the console to have the band diagram calculations. And because for the reference one in the papers, they list the the plate thickness you can construct directly in console. And that's for the first part. Now come to the optimizations. I have my own code to do topology optimization because document analysis is really expensive. It's as I said, it takes 100 hours, right? I use Patsy to do it together with Slapsy, and one needed to use HPC clusters to do this. And after the
Yeah, I think thank you for this answer. Well, I think we need to go now to the next question. Maybe you have a look to the F&A session. If there is, will come another question that you could answer it directly. So
thank you.
Fengwen, thanks a lot.